Welcome to this Frequency Matters podcast. I'm Pat Hindle, Media Director at Microwave Journal, and today I'm talking with Bob Broughton, Director of Design Engineering, Aerospace and Defense at Analog Devices. Welcome, Bob.
Morning, Pat. Thanks for having me.
So today I thought we'd talk about the SATCOM market because that's a hot topic these days. So what are some of the main trends in the SATCOM market, and how are those affecting the design and test of components?
Well, after the delays due to COVID and various financial constraints, the low Earth orbit market is finally starting to get rolling. There's a few differences between LEO and GEO satellites that are driving those trends. So let's talk about that a little bit. So LEO satellites are smaller than their GEO counterparts. So this enables dozens of satellites to be launched from a single bus at one time. So the satellite itself is smaller, but that means that the available area for solar cells is smaller as well. So we have to be careful about power. The mission lifetime expectation for LEO is more like 5 years than the typical 20 years we see in GEO. So that's a factor. But also LEO orbits only last about 90 minutes. So there's about 30,000 orbits over that 5-year lifetime. That means a lot of temperature cycles and greater excursions in temperature than what you'd see in a typical GEO orbit. So there's a few things that have to happen to make these LEO satellites and constellations really feasible. Size, weight, and power and cost are super important, and even more so than for the GEO case, just because of the number of satellites that are being launched in these constellations. So the ICs need to be highly optimized for the application. System partitioning to exploit the optimum semiconductor technology for a particular function within the signal chain. And you have to have specially purposed packaging to cope with the temperature extremes and the number of temp cycles that these devices experience. So gas and GaN, LNAs, and power amplifiers, these are the technologies of choice for the antenna feed. And these technologies are inherently radiation tolerant. On the beamformer side, we've moved to silicon on insulator CMOS. And this is a great technology for very efficient switching and enables passive structures that are an order of magnitude more efficient than their counterparts that you see in radar and 5G phased array applications where they use more active structures. And the SOI CMOS is also radiation tolerant, so it's a good technology for space. Test and qualification will be dictated by the final customer emission. But it's fair to say that we're getting away from the traditional space QMLD flows and moving more toward new space flows. And just because they're much more economical at the scale that we're talking about for LEO orbits, and they're more compatible with high volume production.
Well, I never thought about that many cycles for that going around the Earth that many times. That's a lot of cycling. So are you seeing more beamforming arrays, and how are you addressing that technology shift?
From the ground side, with GEO and even MEO orbits, mechanically steered antennas work just fine, and they're actually superior in terms of efficiency compared to a phased array. But from the point of view of an aircraft, for instance, LEO satellite is moving at about 1 degree per second across the horizon. So you add the airframe motion and turbulence and the fact that you need to seamlessly hand over from a setting satellite to a rising satellite. All these factors, it's clear that you can't do this with a mechanically steered dish. You need phased array to do this efficiently. So another advantage of phased array is the fact that the antenna can be built conformal to the surface of the aircraft. So you might be familiar with the big wart that's on the back of these commercial aircraft, and that's the mechanically steered antenna back toward the tail. With the phased array, you can make this antenna conformal to the surface of the aircraft, so you get rid of that big lump and potentially reduce fuel consumption and improve the aerodynamics. But it's a pretty tough job to make a beamformer chip that's small enough to fit in the 5mm element pitch that's needed for Ka band. On the terrestrial side, we end up integrating the LNA and PA to meet that challenge, and we've found that we've had to co-design the ICs with the antenna aperture itself. We actually build the antenna to test the ICs, but also to make sure that we can build up the array efficiently. So we co-designed our Ka band chipset with the actual antenna just because of the extreme area challenges. One example, during that exercise, we couldn't find a Wilkinson power divider that met our size and cost requirements. So we disintegrated the 4-to-1 divider that was embedded in our chip designs, and we developed that and released that to the market to enable these small arrays.
So with systems starting to use multiple bands and multiple orbital systems, how does that complicate design and test of these systems?
Well, the development of these ICs is still very expensive, and more so with the deep submicron CMOS technologies. But you can't use the same chip for Ku band that was designed for Ka band, and the payload chipset is very different from the chipset on the terrestrial side. And by the way, the 5G chips and radar chips, they're not a great match for the SATCOM applications either. So how do you achieve scale when the market is so fragmented? So we've taken a platform approach to this market where the digital control interfaces are identical, or at least as close as we can make them to one another. And that's just to improve the ease of use and reduce the software development burden for the system integrator. But we also have a very efficient IP reuse strategy where we design and debug new cells outside of the product development cycle. And once the cells meet their requirements, the design is frozen and we use these as components, and we integrate these into multiple chipsets. So it's just a way to control the expense of these and be able to offer more models. So the LEO emergence has brought scale and economy to phased array. And this is a benefit to MEO and GEO as well, where you can use the same chipsets. The chips don't care about orbit per se. We might use a different LNA or a PA for GEO than we would for MEO or LEO orbits. It's the beamformer ICs themselves are basically the same. And for GEO, maybe there's a different space qualification flow, but otherwise it's the same devices.
So looking at the LEO market and the cost constraints there, are COTS or reduced screening devices sufficient for many applications, and how is ADI managing the mix there?
ADI has a long and rich history in space, and we're trying to drive the shift from traditional to new space as the market accepts these new flows. So today we see a mix of qualification regimes. Our system integrator customers definitely see the cost benefits of near COTS flows, but it's taking some time for the end customers like government agencies and insurance underwriters to make the actual shift. So they'd like to do it, but who's going to do it first? So we continue to offer a spectrum of flows from COTS through what we call commercial space, where we offer radiation testing data and lot traceability, and other options like potentially burn-in and these sorts of things, not all the way up to full mill ball levels. So we expect that once the market gets through, a few of these LEO constellation launches and we get enough experience, the shift will occur for a majority of missions, and most of all for the LEO orbits with the shorter mission lifetimes. With the volumes involved to supply hundreds or thousands of satellites and shorter mission lifetimes, pragmatism will drive us toward lower cost flows and just to improve the economics. But full-on COTS, at the very least, the devices have to be designed on radiation-tolerant semiconductor processes, and someone has to collect the data and know how to exercise the parts during those tests. So there is, we think, value to the customers there, and honestly, the markups for the commercial space flows is quite small compared to the full QMLV flows.
And looking ahead, how do you see the market changing over the next few years with the launch of so many satellites and networks?
Yeah, so we see Starlink is already delivering high-speed internet to areas that are underserved by cable and other communication methods, and for actually very competitive subscription costs. So this trend is going to continue with more competition and drive for more capability. But with the cost of the satellites and launch costs coming down, we're seeing even sovereign nations that you wouldn't normally associate with space developing their own constellations. So I think the next wave is going to be building out the 5G NR capability, where you'll be able to reach the LEO satellite directly from your cell phone. Think of it as a network of base stations flying above you. When this comes online, in theory, there'll be nowhere on Earth where you can't receive a cell phone call or download data from. So these antennas are, yeah, again, different designs, this time at L and S bands. There may be some different partitioning and system design choices available at these lower frequencies, but this market's going to be big when it does take off. So the market's going to be very active and lots of opportunity for innovation. And this feels a lot like the cellular revolution that we saw about 25 years ago. So it's really exciting to be working on new technology that will have a profound effect on the world in the next few years.
Yeah, I totally agree. The non-terrestrial network capability added to 5G is going to be a game changer in the long run. Well, thanks, Bob, for sharing with me all your information today on the SATCOM market and like some of the design trends and how ADI is dealing with those. It's always a pleasure to talk with you. So I hope to have you back again in the future. To our listeners, you can find more podcasts at podcast.microwavejournal.com. Thanks for listening.